is we're just going to do like one section out of chapter 15. So I'd estimate like, like 30 minutes-ish of attention is all I'm asking for. I would have given a delta math or something, but we legitimately have nothing to delta math on because it's just, we're just starting something new, You hate the delta math, so you're glad that we're not doing that. Fair enough. All right. Now, for my understanding, none of us have done like exponential or logarithm in your Algebra 2 class, right? Nobody got that far. Maybe some of us that maybe came down from honors might have. But I think if you were in regular, I don't think we did exponential or logarithmics yet. Is that right or no? Yes? Okay. If you came down from the honors, I think you would have done that already. So in section 1, we're going to talk about two types of functions, exponential and logistic functions. Later on in this chapter, we'll also talk about logarithmic functions. And I'll be frank with you, as far as topics go in second semester, if you haven't done this before, this tends to be a bit of a challenge for some students. I'm going to go slow because I know it's the majority of us, it's the first time seeing this, unlike the previous couple of sections where I know that you had done this before in your Algebra 2 class, where I, didn't do everything in as much detail as maybe I would if it was your first time through seeing something. So here we're going to go slow, okay? We're going to make sure we do a good job. So we're going to start by talking about exponential functions. And when I say an exponential function, that means it's something that we can write in the form a times b to the x. Notice the location of the x is in the exponent. Everybody catch that? That is our defining characteristic of an exponential function, is the variable is in the exponent, versus a polynomial or a power function that might look like this, right? So that's like this could be a polynomial or maybe a power function depending on what the value of that exponent is. The exponent's a positive whole number, it's a polynomial. If it's any decimal, any real number, then it's a power function. But there, the x is the base of the exponential. So I want to give some names for some of these things, for these parts of the exponential. This coefficient here is sometimes called the initial value. The b is the base. We call that the base of the exponential. And then the variable there is the exponent. Now, a couple of things that are assumptions we're going to make when we talk about exponential functions. is that we're not going to count it as an exponential function if that coefficient is 0, because 0 times anything is just 0. That's a constant function now. We don't want to include that. So that leading term, or that coefficient out front, has to be non-zero. And then our b, our base, is got to be a positive number and can't be 1. So if b were 1, it'd just be like 1 to the x, and 1 to any power is just 1 still, right? So we don't, and then that just becomes a times 1. That's a constant function. We don't want to include that. If b was negative, remember x can be any number, right? Because it's the variable. So it could be things like a half or a fourth or a sixth. Those are all equivalent to even roots. You can't take the even root of a negative number. That's undefined. So if we allowed b to be negative, you'd have like infinitely many discontinuities inside of this function. It would just be like a gross, disgusting nightmare of a function and really well defined, or like really poorly defined. So we just don't even want to consider that. Will?
So if b can't be 1 and it has to be positive, why does b being greater than 0 matter?
Because you have to include things like a half or a quarter. Like b could be values that are less than 1 and bigger than 0.
Oh, okay.
Right? Like 0.1 or 0.2. We still want to include those numbers. Those are fine. And in fact, will be really important. We'll talk about some specific situations where like a base of 1/2 is like real world applicable. So we have that. I want to remind you guys about some of our rules for exponents. So like, I'll just write it, yeah. Right, so if we multiply two numbers with the same base, we add their exponents. And if you have the product of two numbers raised to a power, you can take the power of each of those numbers and then multiply them. These are the big two that we have to really be cognizant of, because these tell you how to multiply things with exponents in it, right? So if you have the same base, you can add the exponents without changing the base. If you have the same exponent, you can multiply the bases. So for example, if I have like 2 to the 3rd times 2 to the 5th, that can just become 2 to the 8th. Or if I have 2 to the 3rd times 3 to the 3rd, that can just become 6 to the 3rd. So when the exponents are the same, you can multiply the bases. That changes. When the bases are the same, we can add the exponents, but the base stays. You're never going to be able to multiply numbers together that have different bases and different exponents. So for example, if I have like 2 to the 3rd times 3 to the 2nd, there's nothing to do there, right? Can't simplify something like that. Does everybody feel okay there? Now, the reason I want to emphasize this is because a real common mistake I see students make with exponential functions is if we write something like -2 times 4 to the x, I will see frequently students want to write that as -8 to the x. Super wrong, because the exponent on 2 is 1, the exponent on 4 is x. Shouldn't multiply the bases because the exponents are different. The base for -2 or the base is, one of the bases is 2, the other base is 4, so we can't add the exponents either. There's no simplification that can be done for an exponential function that looks like this. Do you guys see that? Actually, I'm going to make, yeah, that's fine. I mean, there is a way to do some simplification here, but it's beyond the scope of what I would ask you to do. So let's do just some simple evaluate. So I'm going to say my f of x is just this -2 times 4 to the x that we've been talking about it. And we're going to evaluate some stuff here just to practice and remind ourselves of some of the other rules for exponents that maybe I haven't touched on yet when I talked about those two. But those are the two like most important ones. Those are the most common mistakes I see students make, are dealing with that stuff. So I wanted to make a special point of doing that. All right, when I have something that says like f of 2, what is that telling us to do? Yeah, we're just plugging 2 in for x, right? So that would mean -2 times 4 squared. 4 squared is 16, and -2 times 16 would be like -32. Everybody feel good there? Okay, if I do f of 0, that's going to be -2 times 4 to the 0. What's 4 to the 0 equal?
0.
Not 0. Not 4. 1. So we recall like x to the 0 is equal to 1, you know, for all x other than when x is equal to 0. 0 to the 0 is like undefined. Okay, that's another rule of exponents. So now we have f of -3. So that's -2 times 4 to the -3. What does it mean to have a negative exponent? Do you remember what that means? Means you make a reciprocal, right? So that means 1 over 4 to the positive third. 4 to the third is 64. So if I multiply that through then and reduce, I'd have like -1 over 32. So our rule of exponents that we took advantage of there was that guy, right? Remember that? Or maybe you did, maybe you didn't, but you do now that I show you. Okay, that looks familiar. That's the minimum there that I'm looking for. Okay, next is f of 1/2. So that's going to be -2 times 4 to the 1/2. What does like a fractional exponent mean? Well, when I have a unit fraction like 1 over something, that's going to indicate that it's a radical. The denominator of that unit fraction tells you the index of the radical. So because this is 1 over 2, the 2 part tells me that we're talking about a square root. And I know the square root of 4, well, that's just 2. So again, the rule there is that, x to the 1 over n is just the nth root of x. So far so good. We're doing okay. Okay. Just doing this mostly to review these exponent rules because it's been a minute since we've worked with them in this kind of, level of depth, and they're easy to kind of blur together about how you manipulate these things, and it'll be important as we work through exponentials that we remember these things. So the next one is f of -3/2. So that's going to be -2 times 4 to the -3/2. So I would start by dealing with the negative exponent. Everybody's okay there? And now I know that one of my properties of exponents was this, right? Was if I have an exponent of an exponent, that turns into the product of the two exponents. So that's what I'm going to think about with the 4 to the 3/2. I'm going to think about it as 4 to the 3rd to the 1/2, or I could think about it as 4 to the 1/2 to the 3rd. Which one of those two do you think I'm going to I want to think about it as? Which one of those looks better, this one or this one? The one on the right, correct? Because hopefully you recognize 4 to the 1/2 is just the square root of 4, which is just 2. Yeah. So that's 1 over 2 to the 3rd. Everybody feel okay there? And then if you recall that oops. We can do that, right? Or really what I would just think about it is just that. So I'm left with -1/4, or -1 over 2 squared. So I think that sums up most of our major rules of exponents, just kind of running through those examples. Do we feel okay with that? Okay. So one of the other early skills that we're going to be looking at is taking a table of values and trying to turn that into an exponential function. Now, we've already kind of done this once early on, right? Do you remember going and doing this back when we did, I think it was chapter 12, we did the modeling? So you can still use your calculator to do this, just doing exponential regs, that's fine. But I'm also going to show you how to do this by hand for certain situations. Okay? So the key observation here is that one of my x values is 0. Actually, I should just circle. If I have that, then this problem is very easy. Bless you. So I want to write an equation that looks like this. Everybody's okay? If I have the point 0, 3, I can plug 3 into y and 0 in for x. B to the 0 we know is just going to be 1. So we're left that a is equal to 3. Everybody feel good there? Now I can choose any other point here. Well, let's be honest. Mr. Kulik's not feeling like making his life any harder than possible. I would, if I have the x-coordinate of 1, that's the next easiest one to deal with. Like, give me some of that. So again, I'm going to start with my y equals a times b to the x. I have y is 15. I now know a is 3, and I know x is 1. So I can solve now for the b. So if I just divide both sides by 3, I get that the b is 5. So if I put those together, I have y equals 3 times 5 to the x. Can I just call that y equals 15 to the x? What do you think? No is the correct answer. Thank you for all the very subtle head shakes that I saw going on. So that's the easiest case scenario where you have x0 in the table. That allows you to find a immediately. And then you just have a one variable equation to solve where you just pick any other point, plug in for x and y, and you can find b. And then you just got to rewrite your equation. What's a bit more challenging situation that you'll see is if you're given only 2 points. So these would be the only 2 situations that you'll see, is either the case where we had a whole table, but 0, x equals 0 is one of the values in our table, or something like this, where you have just 2 points. So again, we want to write an equation that looks like this. So I would start by just plugging in the x and y. Thank you. Then I'm going to use each point, x and y, and plug them both in like this. That's going to create a system of 2 equations. Jenna, this is your pass. Whenever you're ready. Now, you guys probably spent a whole chapter in Algebra 2 talking about how to solve systems of equations, right? You did substitution or elimination or graphing or use the matrix maybe. But there were lots of things that you could have seen, right? This system here is a little bit different than the ones you looked at in Algebra 2, because in Algebra 2, in your systems, your variables were being added or subtracted to one another. You had 2x plus 5y equals 7, and then 3x minus 6y equals 12 or something like that, right? Here, the variables aren't being added or subtracted to one another, they're being multiplied. So I would still do elimination, but the way we're going to do elimination, instead of adding 2 equations together to get the variables to cancel out, we're going to be dividing one equation by the other. So I'm going to label these equations as A and B, and I'm going to divide one equation by the other. Now, it doesn't matter which one you divide, or which one is the top of the division problem, which one is the bottom of the division problem. But if you're careful, you can make that division problem a little bit easier by making a good choice here. So the way I'm going to choose the top is I'm going to pick the one with the bigger exponent on the b. So I'm going to do b divided by a because the equation b has the bigger exponent. -1 is bigger than -3 because it's further to the right on the number line. So if I do that, I'm going to have the left-hand side of b over the left-hand side of A, and then the right-hand side of B over the right-hand side of A. Does everybody feel okay with what I've written here? So 12 over 48 just reduces down to 4. Everybody's okay, or 1/4, excuse me. We okay with that? Okay. On the right-hand side, the A's just reduce out. And then to simplify the B's, I'm going to have the numerator minus, or I'm sorry, the exponent from the numerator minus the exponent from the denominator. So what is -1 minus a -3? That's just 2, right? So I have 1/4 equals B squared. That's an equation I can solve for B. So I'll square root both sides. Now, how do I take the radical of a fraction? Excellent. So again, the rule that, was it Lucy I heard? Yeah, good job. Quoted is that we can just square root the top and bottom, so we can break a radical. So the square root of 1 is just 1, and the square root of 4 is just 2. But because we square root both sides of the equation, we get a plus or minus on that, right? But remember our definition for exponential functions. I'm going to scroll back up to remind you. What did we say about the base? Can't be negative, can it? So guess what? About that plus or minus down there, what are we going to do? We can discard the minus. So now that we have an answer for B, I can plug that in back to either A or B. So if I look at the two equations, the one that looks more appealing to me is putting it into equation B, because the exponent on the B is closer to 0 there. Everybody's okay with that? What is 1/2 to the -1 power? If I have a fraction to a negative exponent, it makes a reciprocal, right? It just flips it. So if I divide both sides by 2, I get A is equal to 6. So if I put those both together, we can do that. And it is standard practice, if you have a fraction to an exponent, you want to put the parenthesis around the entire fraction so we don't accidentally think it's like 1 to the x divided by 2, that it's 1/2 to the x, right? So I will be picky about a parenthesis there around a fraction with an exponent on it. So be aware, I will be picky about that. Now, of all the different bases for an exponential function, so when I say base, what I mean is B, there is a value for B that's of particular interest to us. That special value for B is the number 2.71828, yada, yada, yada. And we're going to call that number, we're going to give it a name. It's an irrational number. It can't be written as a fraction. Its decimal continues on forever. There's no repeating pattern to that decimal. We're going to give that number a special name. We're going to call it E. So the letter E is that number. We've given that number the name E after a mathematician. So it's named after the mathematician Leonhard Euler. Who did let's see, he was like a 1700s mathematician, and did just a whole bunch of really important foundational work in algebraic area. I'm not going to talk about kind of where that number E comes from right now, but when we'll go a little bit further, I'll kind of circle back and talk about that. But this is an irrational number, which means you can't write it as a fraction. It's a non-repeating, non-terminating decimal. And the reason this is a special value is that all exponential functions can be written as y equals a times e to the kx. And the reason that's really nice is because if all these exponential functions have a constant base, we can all write them with the same base, makes it much easier to compare the exponential functions. So that's the point of this value E, is that it allows us like a skeleton key to rewrite any exponential function so they all have the same base, which makes comparison between them much simpler. Does that feel okay? Contextually, why we care about this number? So when we talk about exponential functions, we typically will talk about two types of exponential functions. So we have exponential growth, and then we have exponential decay. So exponential growth is going to look like this, or like that, where it's increasing from left to right. Everybody's okay with that? Notice here that we have a key feature. We have a horizontal asymptote at y equals 0. You guys see that? That's this line right here. So, if I have my exponential function written in this way, it's going to be exponential growth if a is greater than 0 and b is greater than 1. Or, that's going to be like the red graph, if a is less than 0 and b is between 0 and 1, that's the green one. Yes, of course. And then if you have a oops, if you've written it this way, here it's much simpler. Here you need a greater than 0 and then k greater than 0. Or a less than 0, k less than 0. And again, this would be equivalent to the red one. This would be like the green one. Now a decay is going to be decreasing as we move from left to right. So it's going to look like one of those two. So it has the same key feature, right? We still have to see the same horizontal asymptote regardless. And then if we are written in this form, I can tell it's a decay just by looking at the A and the B. So if the A is positive and the B is between 0 and 1, that's like the red graph. Or if the A is negative and the B is greater than 1, that's like the green graph. And if we're written with an E, that's if A is positive and K is negative, or if A is negative and K is positive. Again, that's like the red graph, and that's like the green graph. So you notice that if A is positive, they're just like the opposite parts, right? And then if A becomes negative, actually do that, right? That they're just like flippy flopping. You guys see that? And the same thing kind of happens down here, right? And I think we're going to stop here. You guys are, look out to lunch here. That was enough, I think, for today. We'll finish up this section and then do section 2 next class. So I still have a little bit more to do on here. You can start the homework for this. It's 1 through 16. There's probably stuff you can do if you're like itching to get something done, or you have a busy week, or you're going to be gone on Kairos or something. You're like, I think I want to get some of this stuff done before I can go. You can start in on that. When it gets to a point where you're like, I just don't know what to do with this, you can stop. But I would say the first 10 or so problems you can probably do without any problem if you've paid attention to today and you're itching to get ahead. If you're going to be here all next week, don't worry about it. We'll just finish up what we're talking about next week, and that'll be that. Sound okay to you guys? Okay. All right.